Our learning goal is still the same as it was yesterday. It's just that our rational exponents are going to have a little bit different look today. So yesterday, when we were learning how to evaluate expressions with rational exponents. First of all, what does rational mean again? What should we expect if it's got a rational exponent? A fraction. Yesterday, when we were doing it, every one of our rational exponents had a 1 for the numerator, didn't it? It was like to the 1/3 power, to the 1/4 power, or to the 1/5 power. It always had a numerator of 1. Okay, well today, when we are dealing with them, we're going to have our fraction exponent. If it has a numerator greater than 1, then we need to know what to do with that because it, we have an extra step in there that we didn't have yesterday. So first of all, when that numerator is greater than 1, when it's not 1, we need to rewrite it as a power to a power. Because remember, what's the shortcut for when you have a power being taken to a power, such as, if I have 2 to the 3rd power, that power is being raised to the 2nd power. What's my shortcut for being able to say what that would be evaluated as? If I have 2 to the 3rd power, let me just write it up here. If I have 2 to the 3rd power, and I'm raising that to the 2nd power, what's my shortcut, first of all, for getting that?
Take 3 times 2 the exponent 2 outside the bracket.
Yeah, so I can take the 3 times the 2, I take those 2 exponents times each other, and I say that becomes 2 to the 6th power, because 3 times 2, okay? And so that's our shortcut for when we're taking a power to a power. Well, it's kind of like what we're going to do today then, is we're going to take it and we're going to work backwards. We're going to go back to that state so that we know what to do with it, okay? So what we're going to do is it says, first we're going to write it as a power to a power. So this is going to seem like I'm almost, talking Greek or something, but it's B. B being the what again? What do we call that? The base, yeah, it's the base. When B, the base, being raised to the m over n power, can be rewritten as B to the 1/nth power, that being taken to the m power, to the m power. Because here's what would happen. If I had B to the 1 over n power being raised to the m power, remember the shortcut says do what?
Times.
Multiply those. So you take B and you multiply 1 over n times m,
You put m over
and you
1
put m over 1,
to get m over
and you'd end up with m over n. It would take you back to where we started over here, wouldn't it? So we're undoing this when we write it as a power to a power, because when we write it as a power to a power, now we're going to be able to evaluate what the power inside the parentheses is. We'll be able to evaluate that, and then we'll take that to the power that's out, the exponent that's outside of it. So in this case, this is really called the nth root of a number. So we're looking for the nth root of the base, and then we're raising that to the m power. So we're looking for the nth root. Whatever our denominator is, we're going to look for that root, just like we did yesterday. And then we're going to take that, once we find out what b to that nth power, what the root of that is, then we're going to take that to that power that's outside of it. So I have an example worked out here. 16 to the 3/4 power. We can rewrite that as 16 to the 1/4 power, 1 over n. And then our m, our numerator, moves out and becomes the exponent on the outside. Because would 1/4 multiplied by 3, would that take us back to 3/4? Would it? Because when we rename it, we better rename it properly. So if I multiplied 1/4 times 3, would I get 3/4? What should I do with that 3? Put it over 1. 1 times 3 is, and 4 times 1 is. It would take us back to this, wouldn't it? Okay? So we want to make sure, first of all, we rename it properly first as a power to a power. Then we say, okay, well, 16 to the 1/4 power really means I need to find the 4th root of 16, which is what, by the way? What times itself 4 times gives you 16?
2.
2.
Yeah.
That is 2. 2 times 2 is 4 times 2 again is, times 2 again is 16. So the fourth root of 16 is 2, and that 2, so what was inside the parentheses became 2, and that 2 now has to be cubed. And 2 to the third power is 8, isn't it? Okay? Okay, why don't you just, you got erasers on those pencils? Why don't you just do the first step? Just rename it as a power to a power. Just try that. See if you can rename 25 to the 5/2 power. Rename it as a power to a power. That's all I want you to do. Okay, who's our brave soul that's willing to share what that would be as a power to a power? Abby, what do you think? Like that? Okay. Okay, how many of you agree with Abby that would be its new name as a power to a power? Yeah, that is it. So the 2 is our n, remember, so we have 1 over n inside of our parentheses. And, oh, that's really a big eraser. Might as well erase the whole thing now. Okay, so 25 to the 1/2 power, that's being raised to the 5th power. Well, 25 to the 1/2 power really means what? What root of 25? Square root. The square root of 25 raised to the 5th power. Oof, I think our power table is going to come in handy here. Okay, what is the square root of this? What is the square root of 25? 5. Okay, so we get 5 for our parentheses, and now that's going to get raised to the 5th power. Now, if you need to keep parentheses around these so you can say, you know what, where did that 5 come from? It came from the parentheses prior. So the square root of 25 is 5, and now we have 5 to the 5th power. Unless you just happen to know that off the top of your head, your power table might come in handy right now. Michaela? 3,125. Everybody agree? You got the same thing on your power table? Okay, I want us to notice something different between number 1 and number 2. We use the same process. But I want you to tell me something that's different about the fraction exponents, those rational exponents that each have. The first one started with a rational exponent of 3/4. This one started with a rational exponent of 5/2. How do they differ? What's different about them? So it's an improper fraction, so in other words, it's a number greater than what? 1. 5/2 is greater than 1, isn't it? How about 3/4? It's less than 1. Notice something that happened then. See something else then that happened, because here we had a rational exponent of less than 1, and our evaluation, our value we got was, what relationship does it have to the base? Larger or smaller? Smaller. Okay? What happened in the second one where the rational exponent was greater than 1? It got bigger than the base, didn't it? It ended up bigger than the base. So here it ended up smaller, 8 smaller than the base of 16. Here, 3,125 is a lot bigger than 25, the base that we started with. So maybe we could start assuming that if the rational exponent is greater than 1, our final answer better be what? Greater than the base. If our rational exponent is less than 1, then our final answer should be less than the base. Should we start assuming that and see what happens? Okay, let's try number 3 then. Kelvin, I want your expertise. I want you to tell me how I'm going to rename this as a power to a power. You got it?
Yeah, sure.
Okay, I'm ready.
27. 1/3.
To the 1/3 power, okay.
Yep. And then 4.
Raised to the
To the
4th power.
power.
Okay. You guys agree with that? good job. Okay, now, notice we started with a rational exponent what? Greater than or less than 1? Greater than, so according to, going by our assumption we just made a little bit ago, should our final answer be greater than 27 or less than 27? Should be greater than, shouldn't it? Okay, let's check it out then. So 27 to the 1/3 power really means what? The third root of 27. Find the third root of 27, and then after you have that, take it to the 4th power. Or in other words, the third root, now we know that that means what times itself 3 times gives you 27. 3, okay? So the third root of 27 becomes 3. And now we have 3 to the 4th power. Anybody got that one memorized yet? 81, yes, it's 81. Did our theory hold true? So far, it seems like what we seem to think. Now, let's just do some checking out our calculator to make sure we're right. Okay, would you do that for me? Would you check out number 2? Check out number 3. Then maybe we'll go back and check out that one that had already been worked for us and make sure that that one's right. So take it actually to the power and let's find out. The square root. Yeah. You do this right here. So you would use the second. So that's only when you're finding the square root of something. Oh, that's not, that square root is different than power. You don't take it to a power. You need to do the carry power. So power is, yeah, that's raising it to a power. And now, 25 raised. Now you're going to take the parentheses. You would put your 5 divided by 2. 2 means put your parentheses equals, see what it says? So when you're finding the root, you use that key. When you're getting into a power, you use that here. Okay, how do we do? Did we get the right answer for number 2? I just did that one with Mikhail, and it seems like we did. How about number 3? Did we get the right answer for that one? How about number 1? Anybody go back and check out number 1? What's your request here? Okay. Are we right? So I want us to understand, why does it work? Why do we think it works that, you know what, let's just not say, well, this is, she just showed us how to do it and now we know how and we get the same answer the calculator does. Let's reason out why. When that rational exponent, that fraction, is less than 1, why is our answer less than the base? Or, if you're like, oh, I can't do that one, maybe you can figure this one out. Why, when the rational exponent, or our fraction, is greater than 1, does it turn out, our answer turn out to be bigger than the base? Anything times 1 is itself. Okay, so anything to the first power is itself. Is that kind of what you mean? Anything to the first power is itself, okay? What about when you take something to something less than 1 then? What happens? Does it just become 1? So only when it's to the what power does it become 1. So in other words, let's just use that 16 as an example here. When I take 16 to the first power, that is what? 16. And when I go lower than 1, when I say, oh, maybe I'll go to 0, 16 to the 0 power is 1. And then if I go even lower yet, 16 to the negative 1 power is what again? 1 over 16. So it just keeps getting smaller. So when my exponent is less than 1, my answer is less than the base, isn't it? But when I start going bigger, I wonder if anybody knows this one. 16 to the second power. Go ahead, that's your calculator. Help us if you have to. What is it?
256.
256. Look at there, it got bigger, didn't it? So when we had 16 to the 3/4 power, that's somewhere between 0 and 1, isn't it? So then our answer should have turned out somewhere between 1 and 16, did it? 16 to the 3/4 power. 16 to the 3/4 power is in here somewhere, right? Do you agree?
Yes.
And then our answer of 8, is it fit properly in there? Yeah. Okay. Well, what do you suppose then? I wonder what 16 to the 5/2 power is. What is 5/2 as a mixed number?
2 and 1.
2 and 1/2. So this is really the same as 16 to the 2 and 1/2. Oopsie. 2 and 1/2 power. And that answer better be bigger than 256, smaller, same. It better get bigger, it better increase. Okay, well let's try it then. Let's see if it does. 16 to the 5/2 power means what again? What's its power name? Power to a power name?
16 and then in parentheses. 16 to the second power in
16 to the
fifth.
Yeah, 16 to the 1/2 power in parentheses to the 5th power. So this means what again? This means what? The square root of 16. And the square root of 16 is 4. Right? Do you agree with me? And 4 to the 5th power, anybody happen to know what that is? 24, did you say? Huh. So it's starting to make sense why this happens, doesn't it? So when it's to the first power, it's just itself. When it gets smaller than 1, it starts getting the base, the answers get smaller than the base. When it starts increasing beyond 1, then it's going to be getting larger. So where should 16 to the 3/2 power fall between? 16 to the 3/2 power, I'm going to write it here, 16 to the 3/2 power, where should that answer fall between? Abby?
16 to the 2nd and 16 to the 5/2.
So it should be somewhere in between these two? So it should be somewhere between 256 and 1024? Devontae, you want to challenge that?
26, actually.
So it's got, so Abby was thinking that maybe because it should be between these two powers, it would be between these two answers here, 256 and 1024. Abby, are you changing your mind about yourself? What do you want to change it to?
Between 16 and 3. Yeah, 16 and 16 to the 2nd.
So it should be somewhere between 16 and 256. Because what?
Because it's getting smaller.
So when we look this way, it's getting smaller. So is 16 to the 3/2 power then, is it in between 16 squared and 16 to the 1st power? What is 3/2 the same as? 1 and 1.5. Is 1.5 between 1 and 2? Okay, so then we're thinking that this answer better turn out between 16 and 256, right? Well, we already kind of did this over here. We just changed this to a 3, right? So now what would change? The 5 changes to a 3. 4 to the 3rd power is 64. So, you know what? I don't want you just to get answers. I want you to reason out, do I have answers that are good? Do they make sense to what I was doing? I was raising it to a power greater than 1. Wait a minute, my base was 16 and I got 4? Or the rational exponent is less than 1 and the base was 5? And you got 125 for your answer? I want you to reason out that, you know what? Just getting an answer isn't good enough. Okay, how about number 4? 1 to the 4/5 power. Faith, you tell me how I would rewrite that as a power to a power.
1 to the 1/5 to the 4th power.
Okay? which really means then 1 to the 1/5 power really means find the what? Fifth root of 1. And then what are we going to do with that? To the 4th power. And then the 5th root of 1 is 1. And 1 to the 4th power is 1. Isn't that crazy? Do you think there's any sort of a conjecture we could make about raising 1 to a power? Always going to be 1?
No matter how many times you take it times itself, it's always going to be 1.
So no matter how many times you take it times itself, which would be the outside number, right? No matter how many times you take it times itself, it would still be 1, as long as you're taking 1 times itself. Well, and so basically what we need to also decide then is any root of 1 going to be 1? So if I ask you to find the 7th root of 1, or I ask you to find the 10th root of 1, or I ask you to find the 2nd root of 1, or I ask you to find the cube root of 1, is it always going to be 1?
Yes.
Because you remember root means how many times you multiply something to get that base of 1. So can you multiply by anything else other than 1 times itself to keep getting 1? No. So what conjecture do you think we can make here? You can be like, don't make me show all the work for this, because seriously, LeGrand, this is always going to happen. 1 to any power is going to be 1. Doesn't matter if it's larger than 1, that exponent. It does not matter if it's smaller than 1. It does not matter if it is 1 itself. Then how about 0? What's 1 to the 0 power? 1. You know what? The table for powers of 1 is going to look like this. 1 to the negative 7 power is 1, because it's 1 over 1 to the 7 is 1. 1 to the negative 6 is 1 to the negative 5 is, okay, I'll skip over a few. 1 to the 0 power is, 1 to the 3rd power is, 1 to the 100th power is. Yeah, that table would look like it just have all those 1s with it. So we're going to make this conjecture. We're going to say, you know what? Take 1 to any power you want. I don't care if it's negative, positive, fractional, whole.
Nathan Tucker, Orange, the junior high office.
My answer is always going to be 1. Okay? How about 0? Something that we can say about 0. Will it always be 0, or will that be 1? Well, let's try it. What does 0 to the 5/6 power mean?
0 to the 1/6 to the 5th power.
Okay, power to a power name. 6th root of 0 is, in other words, what times itself 6 times gives you 0. That we're going to take to the 5th power. What times itself 6 times gives you 0? 0. So 0 is the 6th root of 0. And 0 raised to the 5th power is 0. So what conjecture do you think we could make this time?
Anything times 0 is 0.
Well, that's a difference, you know, that anything times 0 is 0, but that's called the multiplicative property of 0. When you multiply by 0, you will get 0. We're working with powers. What conjecture can we make about powers, do you think? We just made the conjecture that 1 to any power will always be 1. Can we make that conjecture about 0? Will 0 to any power always be 0? Let's try some on our calculator. You guys pick. I don't care what you pick. I want somebody to pick fractions and somebody to pick, you know, whole numbers. Just put something in, 0 to a power. Hey, would somebody do me a favor? Would they do 0 to the 0 power also? 0 to the 0 power is error. It's not 1. I thought everything to the 0 power was 1. Isn't that what we learned? Okay, Aurora, what'd you put in?
I put 0 to the 5/6.
Okay, 0 to the 5/6 power, and that's what we did, and did you verify it was 0? Yeah, okay, well good, we checked out on the calculator anyway. What did you put in there, Calvin?
0.
0 to the 0 power, what happened?
You got 0?
You had 0?
Oh no, I got error. Yeah.
Is that the same thing? 0 or error, are those the same things? Okay, so which one do you want to go with, Calvin? Which one do you want to go with? I'm not trying to convince you of
I'll go with
anything.
the same thing.
What's the same thing?
Error and 0 are the same thing.
Error and 0 are the same thing.
Do you see
Yeah.
error on the number?
I don't know.
Yeah, if, that would mean then you're kind of saying that another name for 0 is error. No, it's not.
What's fine is error.
No solution.
So, what did we learn back when we were doing the 0 property of exponents? We were saying, when you take something to the 0 power, it will be 1, except which base cannot be taken to the 0 power? 0 can't be. So anything taken to the 0 power except 0 itself is 1. So, did anybody take 0 to a negative power? Would you try it for us? 0 to the negative 2, 0 to the negative 3, I don't know. Can you do that? Ooh, so we can't do negative powers either.
Mine says domain error.
Oh, domain error, what's that? Oh, another name for the first and last name of error? Domain error means you cannot have negative values for x. In other words, your exponent cannot be a negative. So we have, if we're going to make a conjecture, we're going to make a proper conjecture to get out of showing the word. What conjecture can we make about raising 0 to a power?
It will always be 0.
So raising 0 to any power will always be 0,
Except 0.
except 0. What about negative powers? Could we do that?
Any positive.
So just any positive, yeah. The only conjecture we can make for 0 is when you take 0 to a positive power, it will always be 0. Yeah, okay, so we gotta make sure we understand, you know what, there are things that we can always count on. But we have to be able to understand what is the domain, Noah. The domain for taking 0 to a power, the domain is positive numbers only. You can only take it to positive powers, okay? So that's the conjecture that we can take for that one. Okay, let's do this check it out problem here, page 399. Would you open your books even though I do have it written there? Let's just see what it's about here. Oh, this goes with the example 3 that's right above it. This is at the very bottom of the page where it says the approximate number of calories, capital C, that an animal needs each day is given by the equation C equals 72 times m to the 3/4 power. What's m representing in that equation, Claren? Noah?
The number of calories.
Nope. Abby? The animal's mass measured in what? Kilograms. Okay. Find the number of calories, which would be what? Capital C in that one. That a 16-kilogram dog needs each day. So look at what they did. Where did they put the 16 in for? In the example problem in the book here. Example 3. Where did they put the 16 kilograms in? For little m. That's how much the dog. That's how much the dog.
8.
Oh.
Needs each.
No. No. Go back and read. Read to
That's
yourself.
how much a dog weighs.
That's how much the dog weighs. It's a 16-kilogram dog. It's how much it weighs. So we put it in for little m for mass. And then we're going to figure out how many calories this dog can have in a day so that it is healthy and not, starved or overweight. So how many calories does it turn out that dog needs per day to maintain its health? How much?
576.
Yeah, 576. Boy, I sit down and eat that in just like 5 minutes. Not even. Okay, so let's do number 3 then, on below it. Find the number of calories that an 81 kilogram panda needs each day. Okay, so what's our M equal this time?
81.
81, yeah, 81. That's how much the panda weighs. So we're gonna substitute in for little m. Order of operations says take 72 times 81, or take 81 to the 3/4 power. Yeah, powers before multiplication. So we're going to leave that 72 alone right now, and we're going to do our renaming 81 to the 3/4 power as a power to a power. Tori, I want you to give me a, what do you think it would be? Because I know you got it. 81 to the what power? No, we're renaming it as a power to a power.
Oh, 81 over 1/4.
81 to the 1/4 power, yep, and then
3.
to the 3rd power, yeah. Okay? So now we're really saying that we are finding what root of 81? The 4th root of 81, and that's what's going to get cubed. So we're really looking for what times itself 4 times gives you 81. Noah? 3. Okay, so 72 just keeps coming along. That becomes 3. The 4th root of 81 is 3.
27.
3 to the 3rd power is 27. So now 72 is going to get multiplied times 27. This would be a good time to use a calculator probably.
1,944.
Okay, 1,944.
Yep.
Okay. What are those? Calories. That's how many calories this panda bear gets to eat in a day. Okay. So, hopefully you will also start seeing, as you're working with stuff, you're going to start seeing another pattern developing that you're going to be like, you know what? This is what I can expect to happen also all the time, but I'm not going to tell you what it is at the moment. So, anybody have any questions on any of these before you get started on your homework? We'll do the last thing tomorrow. Okay, I'll take that as you know what you're doing.